So this is Arts Part 2. If you haven't caught the first one, I strongly recommend you go back and watch our first presentation of this from July. That was about a week after we got the sample. Since then, we've had some more time to do some more interesting tests on it. Over here, you can see an example of the scanning electron microscopy. Over here, the energy dispersive spectroscopy, where you can see the elements. We did this testing at the beginning of August, and I've been going through the results of this and trying to come up with some analyses. So just to give you a quick rundown on how this is going to go, I'm going to go over a bunch of pictures of our SEM and EDS pictures. One of the really interesting things that we found was there's these little microspheres that look like zinc-encased lead, and a couple of them are ruptured, which are indicative of some interesting things. We're going to go over the Oak Ridge National Lab Aero report that came out 2 days after we came out with our report. Within their report, they have some interesting stuff about the bismuth nanospheres and the bismuth layer and how it's not continuous but has discontinuities in it. We're going to go over some of the fascinating symmetries we found in the placement, seemingly purposeful placement of these zinc-lead microspheres. We're going to go over the testing that we're currently performing on it, as well as what we are hoping to perform here soon. And then I'm going to go over some speculation as remaining hypotheses for how this material that seems to have been made from elements on Earth could still, in fact, be very non-prosaic, could have originated from someone other than military testing sometime in the 20th century. All right, starting out, SEM and EDS. First off, SEM, scanning electron microscopes. That's for taking pictures really close up. EDS, that's for telling what's inside it for the elements. Here's an example from Jacques Vallée and Gary Nolan back from their paper they wrote in 2022 for NASA. Just to give you an idea on the range of sizes that we're looking at and the density of material that you're looking at. So yeah, we're around the, sub 1 micron range. Also, I'm going to upload at the end of all this, you'll have links to this presentation as well as all of the links that I'm using within the presentation. There's an excellent video from the Sol Foundation that Gary Nolan did recently where he goes over some of their tests on some UFO material. Highly, highly recommend. So for reference, this is the sample we are dealing with. It's very small. Here it is sitting on a penny. Don't worry, the penny isn't contaminating it. Here's the date of the penny, so you can see just how big we're dealing with. It's about 4 millimeters long by about 2.5 millimeters wide by about 0.4-ish millimeters thick. Here is an edge on view for reference. Here's the glue. Oh, sorry. One last thing on this one. So this thing right here, this is epoxy or glue from the previous owner where they were performing tests on it. We have not removed that because we don't want to damage the sample in any way. So we're just leaving it on for now. With that glue, with the whole thing, we weighed it out and it was at about 7 milligrams, give or take 0.5 milligram. So for reference, here's that glue spot here at the back. We're looking at the edge on skinny tip here. You can see some of that layering that's going on the side of this sample. For reference, as we're looking at these SEM pictures, this KV down here, this is like the brightness that you're dealing with. So we're dealing somewhere between 5 kV to 30 kV for our brightness in all of these pictures. So this is about mid brightness here. And over on the side, you'll see size scale in microns for most of this stuff. Here is the elemental composition of that image I just showed you. Don't worry about this for now because we're going to have a lot better ones here coming up. But in that, we have carbon over here in red. You can see that is actually sitting on the testing surface here, not the testing sample. So there's a little bit of pollutant going on in this image. We have other images coming up that are much less polluted. You can see that same surface is a little oxidized. But the important thing to note here is that the sample does seem to have carbon on it. It does seem to have some oxidation on it. And most importantly, though, we see that magnesium there. Ooh, pretty magnesium. Here, now we got the thing flipped over. You can see the glue at the back. We're at about mid brightness still at about 15 kV. We're not very zoomed in. We're going to zoom in, though, on this really interesting spot here. There's a couple interesting spots on the tip here, right? But we're going to zoom in right here. See, it's about 0.4 millimeters, 400 microns thick at the skinniest edge there. So as we're zoomed in here, this area really caught my attention. You can see some of the layering going on here. You can see the stridation of the columnar breaking here. But this area here, this really caught my attention. So these things, they look kind of like these little nano cylinders, and it looks like there's some connective something going on between them. I'm going to present a little bit later in this talk as to what I think is going on with these. First, though, let's do some elemental detection of this area. We have carbon, oxygen, magnesium, and then we got this zinc that's dispersed all over the place. Now, for reference, you can see how the zinc is like up here in the air. That's because this is not bright enough, so it's getting a little bit of extra noise going on up here. But down here, I'm not so certain that this is actually noise. I think we're actually getting some good zinc peeking through here. And I've overlaid that zinc over here so you can kind of see what's going on. So for reference, here's those little cylinders that have some connecting lines going between them over here. This green is the oxidation that is going on the surface. And you can kind of see how we got some lines of zinc, some semi-regular patterns of the zinc. And the reason why I say that's important, this picture down here is from Gary Nolan's YouTube video that I just referenced. And in their samples, he was noting how some of these atoms in their materials seem to have very specific atomic placements. So it's important to keep that in mind, that we have potentially atomic placements of certain elements going on in this sample as well. Here is the rough spectra from that one. Now, important to keep in mind is when you're down here at the 1 to sub 1 keV brightness, anything where your count is below a 1 is potentially noise. There might be something there, but it might also be a big old nothing burger. But right on the edge of that nothing burger, we were detecting some aluminum and niobium. Now, this is the only time that we detected that, so it's likely noise. But at this point, with so many unknowns about this, it's important to keep in mind every single little thing that you are able to observe about this. The important part is we have magnesium and zinc, like we've been saying, and a fair bit of oxidation and carbonization on the edge here. All right, this is the magnesium side, the shiny side, and we can see the edge of it, how it has broken. We are only at 5 keV, so our brightness is turned way down. And right here, this is that delamination layer here, right? So right here, it's like the bismuth magnesium zinc transition zone where it delaminated, where it sheared apart. Good takeaway from this picture is you can see the columnar breaking that we had here. In the next image, I'm going to show you how there's a specific shape or pattern or angular structure to these breakings. Make that in another slide or two. First, though, I want to show something on the bismuth side, on the dark side. We have a couple of interesting geometric structures on here. These bright spots, those are all the zinc line lead. We're going to get to that in a little bit. But first, let's look at these geometric structures that look like they're showing up here. Zoomed way in and enhancing the contrast on those. It looks like we have some very specific 90-degree angle going on within some of these circular patterns going on there, but this one really caught my eye. You can see one of those center cylindrical structures, and you see 3 legs coming off of it. It seems to me like that's weird. I can't say for sure one way or another whether there's something important about that, but it really caught my eye because it seems like there's a semi-regular angle between these 3 legs of this thing. I can't even begin to imagine what's going on with that, though. Just something worth looking into. We're going to be uploading all of these pictures. I'm going to share the Google link drive to every single picture we've taken. So I thoroughly recommend that everyone take a look for themselves and do your own analysis on this. Take your own time and do your own research and see what you can come up with from the images that we are sharing, because these are the most images that you'll find on the internet about Art's parts to date. We have hundreds and hundreds of high quality images of this that we are sharing to everybody for free because we want to get as many eyes on this as possible. All right. Here is, again, the bismuth side. There was one thing about this edge that I thought was quite interesting. Right here, you can see these little divots here on the side in one of the shearing layers. And I thought that was quite interesting. We'll come back in towards the end of the talk, and I'll be showing you some other spots on the surface here, which seem to match that same pattern that you see there. Here we are up a little bit higher, still on the bismuth side here, and we've got the brightness turned all the way up to max at 30 kV. And now you can really see this edge structure here really well. We're focused on this line right here. And you got some of these sharp spikes coming off, but most importantly, you can really start seeing the angles of the shearing that occurred when this thing was peeled off of whatever it was peeled off of. Yeah, I think there is much to be gleaned from observing the edges of this thing and how they break. Now, over here, we're focused on the actual surface. Linda Moulton Howe had one of her scientist friends. They put this thing in a beaker of deionized water and left it there for 40 days. And there was a stream of bubbles, of hydrogen bubbles coming up off of a couple different spots on the sample. And they noticed that the spots where the hydrogen gas was coming off of, it seemed like there was cavitation occurring on the surface. Well, we can see a couple of spots, and in the next couple of slides, we'll note a lot more obvious where some of those spots are. But once again, indicating that this thing seems to react to water and produces it produces some redox reaction. Now, way towards the end of the talk, we may have noted some sodium on it, but once again, it was down at the threshold. So take with a grain of salt, so to speak. It seems more like it's the zinc and magnesium that's getting converted into the hydrogen. Here's another zoomed in example of one of those cavitation zones. So on this one, right here, this is an obvious cavitation zone, as we can see from the oxidization that has occurred in that area. So for this image, you can see the green spots is your oxygen, the blue spots, the darker blue spots is your magnesium, and then these turquoise spots, that's all your zinc. Splitting it into its constituent colors here, you can see how you have oxidations very strongly in that spot there. You can see we have a lack of magnesium in that spot, and we have a lack of zinc in that spot. Also note how the zinc is very thinly distributed. If you've looked into the sample at all in the past, you'll note that Linda Moulton Howe and company noted that there was something like 97% magnesium, like 2 or 3% zinc, right? So there's a lot less zinc than magnesium in this sample. Here is our counts that we got on it. Now, another thing when you're looking at these, when you look up higher, when you're getting the brightness up higher, this is much more reliable area up here. When you get counts up here, you're much more confident down at these lower levels than you are down here. Once again, carbon, oxygen, magnesium, maybe some zinc. No, yeah, definitely some zinc. All right, here's a picture that I have skewed for good purposes here from the first talk. There was something on the bismuth side of the sample that really caught our attention. I think that's on the bismuth side. Maybe it's on the magnesium side. No, it's on the bismuth side. Anyways, this little 90-degree fiber thing here. We were really curious what's going on with this. We're like, is it a hair? Is it a piece of polyester? Is it purposeful and part of the sample? What's going on with that? Well, we did make sure that we got that on the SEM. And as you'll note, we're real dim at 5 kV. But all of these little zinc lead seed microsphere things, those fluoresce. Anything that's metal is going to fluoresce and be really bright. And the fact that this thing doesn't fluoresce at all suggests that it's probably not made of metal. Here it is under the metallurgical microscope. This is at like real colors, so you can get a closer idea of what we're looking at. Here is with some added filters to the metallurgical microscope, and you can see it looks like it has some core material going on in there. Well, I found this picture of white or gray hair under a similar microscope, and based upon these little bumps that you see here on the edges, I'm wondering if some old scientist that tested this might have gotten one of their whiskers on there. Coming up in November, I'm going to be visiting the lab, and we're going to try to hopefully do some live streaming of the sample under the metallurgical microscope. So maybe I'll just pluck one of the gray whisker hairs that studying this sample has given me, and I'll put that on the scope. We'll do some comparison. Here's one last image of that weird fiber going on under there. Now, there could be, you know, cooler explanations, like it could be a fiber optic cable or something, but I strongly doubt that. It's probably more likely a contaminant, I would suspect. All right, we're way zoomed in. We're fairly bright at 20 kV. We're way zoomed in at 1000x here. All of these bright spots, those are all the little zinc lead microspheres that I'm talking about, and you can see that some of them have ruptured. Now that's interesting. That's worth pointing out, and that's something that I'm surprised no one else has observed yet. We're going to get there in just a second as to why ruptured spheres are cool. So on this particular image, you can see we have some weird morphologies going on. There's like this big deal going on over here. We're at 200 microns right here, right? So this thing's like 75 to 100 microns long or something like that, compared to all of these, 15 to 30 micron seeds or microspheres. Here, I'm comparing that with our EDS. So for reference, that seed thing that you saw is right here. I'm going to do a GIF that overlays the two here in just a second. But first, I want to go through what you're seeing on this image. So the yellow, that's the lead. The Arrow report, the Oak Ridge National Lab report, said this thing has about similar parts lead to bismuth, and stopped there and said, so it must be slag. I strongly contest that you should just stop questioning this because you detected lead in it. And here's why. We can see these microspheres, right? So you see a very thin layer of this turquoise zinc here on these guys, very thin layers of turquoise zinc. And then you see the yellow lead coming out and peeking out of the ends there. And for this particular spot where it ruptured, you can see we got like this Mount Vesuvius kind of thing going on of the lead peeking out all over the place. And wherever that happened, we also happen to have oxidation, right? So it seems to me, gonna throw out a hypothesis here, it seems to me that because some of these are ruptured and not all of them are ruptured, that something happened to cause just some of them to rupture, right? So it might be, once again, hypothesis, it might be that they're acting kind of like capacitors, right? And they're getting overcharged. And for the ones that get overcharged, they rupture. It may not necessarily be capacitors. I'm using that as an analogy. It also would explain why you see ones that are close to each other as being ruptured and ones farther away just being overdriven and not yet ruptured. And ones even farther away, not yet ruptured at all. Because when you have a catastrophic failure like that in a circuit board, yeah, you'll have capacitors that are all tied together, all blow up, and the ones farther away don't blow up. But the ones closer to it might be stressed out and be much closer to failure than the ones even farther away than that. Just something to consider. These guys here, the red, that's carbonization. Have no clue what's going on with why we're seeing the carbon in it. I would love to have some other eyes look at this, say why that is. It kind of looks, if I go back, it kind of looks like those might be skin cells, maybe. But the problem with that is that we're at 20 kV brightness. So if this was skin cells, like I don't know. That is not my area of expertise there. It's not. So here's a GIF that I made where it's going to go back and forth between the two and it's going to overlay them. So one interesting thing here is this curve. I'll go back up. This curve here. You can see once again, we got that zinc with the lead poking out, but we have a structure, right? We have like almost half circle, half ring going on there. Anywhere where you see a circle or a line or a right angle, those are spots to pay closer attention to because that suggests potentially purposeful manufacturing. And here it's a little easier to see the ruptured spots as well when we go back and forth. All right, here I'm pointing out some more of those ruptured spots so you can see it a little bit closer. All right, now it wouldn't be fair of me unless I did put this side by side with what slag looks like. I mean, Arrow is saying it's slag. Let's see how right they are. So I went online, and by no means am I a metallurgist, so take it with a grain of salt. But what I found here was this one particular image from this one paper whose link is in the slideshow if you go to the link. That looked a lot like this guy, also in size, right? This is about 100 microns, so this thing's about 75 microns long. Well, that's about the same length of that. This kind of looks similar to this. Maybe it is crushed slag. Except slag has iron in it. Now, right here, this is from the Arrow report. They did say that they found iron, if you can believe the Arrow report. But the amount of iron that they found was very negligible. Over here, as we see in the EDS report for this particular bit of slag, you can see that they had a fair bit of iron. And actually, if you go to the paper, you'll see that it was like 15% iron compared to this that is in the like sub 1% or sub 1/10 of 1%. So something to consider. The fact that we never found any iron in ours suggests that, you know, there's less than a percent of iron, kind of like what maybe they're saying. Compared to slag, you would see much higher amounts of iron. So really important to consider when you're talking about the slag angle, where the heck is the iron? All right, so this same image that we were just looking at, I've split it into the colors here so you can see what's going on. Yeah, we got carbonization everywhere. We got oxidation. There is a serious shadow or lack of oxidation in these two carbonized areas, right? The long guy and the potential skin cell or something. There's also a lack of magnesium in that area, which is weird because we have somewhat of a lack of zinc, but not nearly as much as the lack of oxygen and magnesium in these two areas. Going back to those little arranged spots on the edge that I talked about towards the beginning, here in the magnesium, you can see we have a similar arrangement here of those holes there. It's kind of weird. We're finding similar morphologies in completely different places that seem to suggest that some kind of potentially purposeful arrangement or purposeful manufacturing. Also kind of weird is you see some straight lines going on. Like I just said, pay attention when you see straight lines. Over here, we're looking at the zinc a little closer. There's a couple of interesting spots on this zinc. One spot, you can kind of see like a big like half ring going on here. I'm going to speculate again, throw out another hypothesis again. When I look at this and I think of it through the lens of what if this is advanced technology, which everything about this out-of-place artifact is suggesting it might be. I see microcircuitry. I see micro traces going on here. Take that with a big old grain of salt, right? It might not be, but when I look at this as an electrical engineer, that's what I'm seeing is microcircuitry or micro traces. It's almost like they're using the zinc as kind of like PCB traces of some kind. Just what I'm seeing. You also have some of these long, straight, curved areas, something to consider. Here I'm going to do a GIF going back and forth between the two. You can see how the zinc kind of follows this straight line here. Yeah, once again, thoroughly recommend everybody else. You should go through this for yourself, see what you find. This is also a cool little circle thing here that's both on the zinc and magnesium. You can see that that half moon thing that I was talking about shows up a lot more in the zinc than it does on the magnesium. Here's looking a little closer at the EDS of that. Carbon, oxygen, zinc, magnesium, zinc. Now over here, there's a little spike on the edge here that this image isn't showing, but that is the lead right there that just wasn't being monitored for this particular image, but that's what that spike is. All right, moving on to the bismuth side. Again, this is that same image from before where the brightness is turned way up and you can see the spiky side there. Let's look at the distribution of elements going on there. So because this is the bismuth side, the bismuth delaminated from the magnesium zinc. So magnesium, we got darker blue. Zinc, we got the lighter turquoise blue going on there. You can see the presence of both of them over there. You can see the bismuth all over this, but it seems like you can see all of that zinc poking out from underneath the bismuth, right? Because it's a really thin layer of bismuth and we're turned maximum brightness, maximum penetration depth of the light at 30 kV. You can see we got some oxidation going on. And specifically, there's a couple of spots here where you get a little bit of lead action going on. A little harder to see because it's so bright, but yeah, it's all there. Also, and this is going to come in important in a little bit here, these red spots of carbonization, you see those on the edge, specifically on the points. So something caused this thing to have carbon deposits occur at sharp edges almost like it maybe was in a high voltage environment of some kind, potentially. Just throwing that out there. Splitting that same image up into its constituent parts, we can see, yeah, it's got oxidation layer all over the place. Yeah, it's got a lot of magnesium. The zinc, again, we're seeing that distribution, how the zinc seems to have very sparsely populated when compared against the magnesium. Same kind of goes for bismuth. Bismuth is kind of in between the zinc and the magnesium for how prevalent it is. And because it's kind of dark, it's not shown up on the edge as much. The important part, though, is the lead, especially the lead-zinc comparison, which in this GIF, you can kind of see it. It's moving a little fast, I know. But when I look at this, I see a relationship between the two. Now, yes, the two colors do shift from each other. The lines don't overlap perfectly. But when I look at this, I see a correlation, a semi-mid correlation between those two elements, like we saw previously in the zinc-lined lead microspheres. Yeah. Looking at that under the spectra here, once again, we got the noise floor down here, but we do have the zinc, the magnesium. We can see that we do have bismuth and lead. We're still kind of low. We got our zinc in the more trustworthy area of brightness up here, and then we got the lead bismuth up here, even more trustworthy. Let's zoom in on that. You can see the lead up here is about a little less than half the amount of bismuth. Down here, more in the noise floor, it looks like there's a lot more lead in a ratio of bismuth than up here, but either way, we can see that, yes, it has lead, not nearly in the one-to-one parts that the error report suggests from what we're observing, and less lead than zinc when you really start looking at it under the brightness. Here is the bismuth side. Again, we're going to look at the spectra of this part. This is a separate area of the bismuth side. We're trying to look for how uniform all these elements are distributed throughout the thing. You can see the carbonization is much less bright here, right? We have some brighter areas here along with the oxidation, but it is not carbonized everywhere like it is with the oxidation. Over here, once again, interesting spots is the zinc, bismuth, and lead, and how those all have interesting overlaps when you overlap them all together. I think I got a GIF coming up here of that. Once again, we've got our bismuth lead way up here in the trustworthy area, the zinc. So this image is looking really similar to the previous one that we just saw, showing that it's got fairly uniform distribution of these elements. Zoomed in again, we can see, yes, fairly uniform. We got still, again, the same amount of like a third lead to bismuth, more zinc than the lead. And down here in the noise floor, that, yeah, it looks like there's a lot of lead, but you got to go up here to really trust it for sure. All right, now this part is kind of weird. When you're down here in the noise floor, like I said, you can't always trust it, but you still got to consider it at least. In the noise floor over here for one of these, this is an image that Mark took while he was at the lab. He took like his cell phone over there and recorded the whole thing. And this didn't make it into the report that they gave us, but I thought that was interesting enough to still share. So we have sodium, sodium, right next to the magnesium on the periodic table. And we got bismuth and lead right next to each other in the periodic table. The reason why this is important that we saw sodium, potentially important, is because if this thing was in a really high energy environment, like a gamma radiative environment or a reactor, nuclear reactor type environment, any high energy radioactive environment, you might start seeing some transmutation of elements where heavier elements are being transmuted into lighter elements. So I'm just throwing this idea out there that the magnesium being transmuted into a few artifacts of sodium, or some of the presence of lead that we're seeing, maybe that could have been bismuth getting transmuted into lead. I'm just throwing that out there as an idea. Take it with a grain of salt. Here is another image that I took of that. So in this case, pink is your sodium rather than bismuth like it was in previous images for this particular image. This here is your sodium. And you can kind of see in this super blurry zoomed in cell phone shot that, yeah, it looks like there might have been some detection of that. Yeah. Here's zoomed in even further and even blurrier. Sorry, folks, this is the best I could do with the materials we got for recording. All right, this is from the error report. So in this image, we have our layered structure here. Now, these layerings, you can see our scale here is 200 microns, right? So the bismuth layers that are separating all those, according to this image that they have, you can see that up here, this really bright line, that's your bismuth. And then throughout the rest of this is all your magnesium. And then inside of that magnesium, you can see we have layers of zinc that are not necessarily evenly distributed, right? We have a really bright layer of zinc and then a dispersed layer of zinc, really bright layer of zinc, dispersed layer, and then a really dim layer of zinc. Also important is this bright spot that you see for the zinc and for the lead. Those are the zinc-lined lead microspheres that have ruptured, which is why you're seeing it show up so brightly in those areas. Over here, they claimed in the error report that these vertical lines might have been some carbon-based binding agent. I don't know enough whether or not to say for sure that that's accurate. Because we saw some carbonization on the outer edges of the thing, it makes me wonder if these microfractures might have allowed for additional carbonization to occur rather than saying that that is a binding agent. Maybe it is a pollutant like we saw on the edges. Not sure. Here is another image from the error report. This is really zoomed in, right? 5 microns wide. So up here, if you've looked at like cloud chambers before and you've seen how like radioactive emissions seem to go through materials, to me, this looks kind of like it might potentially be some kind of radiation damage, which if it was in a high energy environment, like we're going to see here in a few slides, it very well could have been, then that would make sense. This is supporting the hypothesis that this thing at one point was sitting in a very high energy radioactive environment. So that's the first part of this image. Second part of this image, all these vertical lines you see at the bottom, Arrow is saying that those are artifacts from the focused ion beam, which may very well be the case. I'll give them potential credit for that. It's called curtaining, focused ion beam curtaining. However, I like entertaining ideas. So the idea that it might not necessarily be curtaining, keep that in mind. So here's some images of what curtaining looks like. And yeah, I can see the relationship between that and this, but there's enough variation between this and this that it just makes me wonder. It makes me keep open different possibilities that it might be something else, especially when we look at these nanowire structures. So like these little cylinders I showed you at the beginning, wow, those sure look like these guys to me, or at least, they look more like that than the curtaining, that we're seeing here. Also, when we look at these vertical nanowire structures that have been built in other experiments, to me, I see more of a relationship there. But, I'm not going to hang my hat on that. I'm just saying, All right, another part of the error report. So this part was really interesting to me. Once again, zoomed way in at 5 microns. This is the reason why Arrow said that they didn't think that it was existing as a terahertz waveguide. So if you had a waveguide that was as discontinuous as this, it would be a really crummy waveguide, right? You'd have all these impedances and resistances that are occurring as the signal can't like propagate normally throughout the thing. And yeah, I'll totally give them credit for that. If I was building a waveguide, if I had to use a waveguide and it had this kind of structure to it, I'd just be shaking my head. It would be so unpleasant to try to use that as a waveguide. Here's a more zoomed in area of here. Now, the sizes of these things, you can see these little nanospheres of bismuth that are scattered throughout the bismuth layer, that are comprising the bismuth layer. That's really interesting. That's really telling of a couple of things. Maybe how it was built, maybe what it was being used for. Here is a random paper I'm going to throw in there where we're talking about bismuth nanoparticles combined with lead. being used to make quasi-crystal matrices. A little bit. I'm going to show you why I think quasi-crystals might be prevalent in the sample. And there's a link to that within the thing too. First, though, I'm going to go down a road that no one else to date seems to have done. So supposedly this sample came from the Roswell crash. That is the multiple angles that we have gone down for tracing the history of this sample. Everything about it, seems to suggest that it does come from the Roswell stuff. And yet no one seems to be addressing that we have purported documents of the Roswell crash that give us additional insights to this. Why aren't we at least entertaining the idea that if this thing did come from the Roswell crash, let's look at documents about the Roswell crash that can support or negate the idea that this thing did indeed come from it. So here are some purported documents from the Roswell crash. Roswell crashes were July 3rd to 5th. So just 2 weeks later, General Twining, purportedly, this document, its veracity is still in question because it's from the Majestic documents, but it's one of the more reliable Majestic documents than some of the other ones. So I'm going to treat it like it's real, like I like to do with Majestic documents. Anyways, in here, they're talking about how inside the wedge-shaped craft that there was a toroid, a donut-shaped tube, that went the diameter of the craft, 35 feet. It was made of a plastic material, and it looked like it was filled with deuterium, heavy water, suggesting that it was some kind of neutronic or atomic engine. Here's another memo from about a week earlier than that, also from General Twining, saying that it was a neutronic engine, that there was heavy water and deuterium present in it. Over here, we can see that they found supposedly, they found a whole bunch of uranium. UF6 is uranium fluoride 6, uranium-235, uranium tetrafluoride, magnesium, maybe like we're finding in the craft, and plutonium, thorium. This whole thing seemed like it was some kind of fusion or fission reactor. Oh, and just for fun, a metal similar to lead with a chocolate brown color. I think element 115 was chocolate brown color, but I don't know one way or another on that one. I just thought that was interesting, the chocolate brown association. Here's another part of that same memo that is really important. Focus on this. They said that when they looked at it under a really strong microscope, that they saw a series of fine grid-like lines intersecting groups of dots that are arranged in circular patterns. Well, guess what, folks? Blammo! We got circle here. We got these straight lines coming off that circle. We got a semi-regular arrangement, circles of these zinc lead dots coming out of this area. Over on this side, we got these straight lines of those little zinc lead dots coming from an area. Well, I started trying to draw some, I'll admit this is crummy, like paint drawing here, but I got some better stuff coming up. But I just thought it was interesting as I started drawing some of these circles on here, how it seemed to follow this natural arc of some of these circles, right? And there was a weird triangle in there too, but the most important part was these straight lines on that one. Over here, we see a bunch of these lines radiating out from this central point here. And I do apologize. These images were kind of skewed from the angle of the camera, so it's really difficult with this. I really wish I could have been there for the testing of this to really zoom in on these pictures a little more, but working with what I got here, folks. So here's five-fold symmetry. These black dots, these are five-fold symmetric quasi-crystals that I'm just overlaying on top of these to try to see how well they overlap. And I'll admit, it's not even close to a perfect one-to-one. I'd say at best we're probably sitting around the 50% correlation from what I'm able to see between these two. And full transparency, I tried overlaying some hexagonal structures over these, and I thought it might be closer to 60%. A little bit closer than these quasi-crystals, but yeah, it's really hard to say at this point until we get the Raman spectroscopy and some other methods that might be even more destructive testing to be able to know for sure at the atomic level whether or not these have quasi-crystals inside of them. Nevertheless, circles of dots arranged. I loved that. I loved that. Here is a GIF going back and forth with some other painted on lines that I was doing. Just trying to see the arrangement. Now, one other thing that I'm going to mention about these is the ratio, and this is why I think it's quasi-crystals are important. The ratio of the distances between these dots, some of those distances between these dots comes really darn close to the golden ratio. And if you see the golden ratio pop up with, you know, vertices like these, that is a really good smoking gun that you're dealing with quasi-crystals. So something that definitely deserves a real good approach to testing this is people need to at least entertain the idea that there could be quasi-crystals present in this, which if this thing, which showed up in 1996, was, you know, being built with quasi-crystalline arrangement of these microspheres. Lou Elizondo, in a lot of his recent interviews, because of his book just coming out, he's been saying it's like finding a fully built 747 in King Tut's tomb. If this thing was built in 1996, it's not super likely that anybody was building that. It's absolutely impossible that somebody was building quasi-crystals in 1947 or earlier. So just out of place artifact. That's all I got to say for these. The zinc, lead, microspheres, and their arrangements. If there's one thing you can take away from all of this as to why this sample deserves people's attention, it's that. Why do we have zinc, lead, microspheres that happen to rupture in weird ways, that happen to be arranged in these specific arrangements on this piece of supposed slag? Here's another image that I think I showed in my last talk. Once again, I was attempting in this one to have 5-fold symmetry. I was showing 10-fold, which is almost the same thing in quasi-crystal world, 5-fold and 10-fold symmetries. I was attempting to show how these colored, because all those zinc lead dots, they actually show a bunch of different colors when you look at them under natural light. It seemed like that some of them had specific arrangements, and it seemed like the distances between those had some ratios, golden ratio distances between them. All right, so here's the testing that we got going on right now. We got gamma ray testing going on. If this thing was in space or in some kind of strongly energetic nuclear environment, it's possible it might still be emitting some of that gamma radiation. So we have it set up right now. It's a really long-term, like 2-month long test where we have it set up next to a gamma detector, and we're just seeing, do we get any counts of gamma off of this thing? There was a really interesting thing that Mark and Michael did where they had this sample sitting there and they shined a flashlight on it with a straw, a plastic straw sitting next to it. And when they shined the light on it, it seemed to get attracted to the plastic straw. Now, that could be tribal electric charging of plastic straw. But the fact that it did that when they turned on the light is suggesting that there might be some photoelectric effects going on here, which if you know anything about UFOs, you know that they tend to show off a lot of light. Like the light seems to be really important. And in my previous talk, I talked about how I think Norway observed that the brightness of the craft seemed to be associated to the function of how they accelerate or decelerate. So really important test that in November, we're going to do a lot more of these tests and try to quantify if indeed there's any photoelectric effects and how strong they are. Upcoming tests. Like I said, I'm going to try to live stream the metallurgical microscopy here in November. Really important test is the Raman spectroscopy. That'll show us if potentially there's any quasi-crystals in there. We want to do some scanning tunneling microscopy, which is going to show us really high resolution if it's a conductor. And then for the parts of it that are not conductive, for the insulative parts, we're going to show some atomic force microscopy. And then the most important one, this is the one that I am just uber excited about. So supposedly, TTSA, they got their sample, and the reason why they got their sample from Linda was because they said that they wanted to be able to test it for the terahertz waveguide stuff, but they couldn't do that at any like public place. Like there was no facility equipped to do that, and that they had to go to the Army to do that. Well, there's plenty of terahertz spectroscopy out there, but there's not a lot of free electron lasers where you have really high intensity terahertz. In fact, that's like what directed energy weapons are, like the kind that the Army might be interested in using and testing. So there is a handful, though. There is a small handful, like half a dozen in the world, public institutions that have high energy free electron terahertz lasers that we are currently looking at to try to be able to test this thing to see if indeed it does levitate, as the rumor mills suggest it very well might under such conditions. Okay, finishing this off, we got some remaining hypotheses for how this sample could be built from terrestrial materials and yet still be an out-of-place artifact. We have Dan Burrish, who is a whistleblower, came out back around 2000, 2005, and he was saying that the aliens are all time-traveling humans from like the deep future. So maybe aliens from 24,000 or humans from 24,000 years in the future, you know, were using terrestrial materials to build their craft and they came back in time, or they came back in time some other way and built stuff. I'm just saying, like, don't throw the baby out with the bathwater. There's a lot of different ways that this thing could still be weird. This is one of those ways, is if there was time travel of some sort involved. Another way, you have breakaway civilizations of some kind. Maybe there was some civilization that was building megalithic structures earlier than 13,000 years ago. I included this picture that, obviously take it with a grain of salt, but the whole face on Mars right next to the five-sided pyramid, right next to some other interesting structures. People have tried to suggest there was a civilization on Mars at one point. Dr. Brandenburg, who's been on here a few times, has talked about his observations that suggest there may have been some kind of nuclear event, two nuclear events on Mars a long, long time ago. Just something to consider, you know, throwing all the ideas out there. You could have breakaway terrestrial civilizations that might not even be human, right? Maybe some marmots or some, you know, dinosaurs or someone, you know, tens of millions of years ago. Maybe they advanced really rapidly and we didn't see any evidence of it in the archaeological record because it happened so quick. Who knows? Throwing out ideas, no bad ideas. Or maybe somebody came here from somewhere else a long, long time ago, and they've been here a long, long time. They got places under the ocean or something. Another idea. We have the interdimensional. Who knows? Maybe the Marvel universe is multiverse is more real than we think, and maybe it came from Earth, just not this Earth. We also have this spiritual side that some folks like to entertain, which is maybe it comes from some immaterial realm and is able to transition into our material realm. And when it does so, you know, whatever could be the case could be the case. Maybe it's using terrestrial materials to materialize here. Maybe it's lots of maybes on that. I'm throwing out 1,000 maybes at you, right? These are all the ideas that others who have come long before me have suggested might be the case for these craft. So things to keep in your back pocket. All right, so we've gone over the SEM and EDS. We've talked about the ruptured zinc lead microspheres, as well as their strange orientations. We've compared it against the Oak Ridge National Lab sample. And within that comparison, we've looked at how those nanospheres of bismuth might be very important. The arrangement or the distribution, discontinuity of their distribution might be really important. We've talked about what we're currently testing and what we're looking forward to testing. And I gave you some of the most wild speculation possible on how this thing might still not be as conventional as we think, right? How could this thing be an out-of-place artifact? What possible reasons could there be for this out-of-place artifact? So take it away. We got ruptured zinc lead microspheres, some of them ruptured like they've been overdriven, and they happen to be laid out in really interesting symmetry ways here. That's the takeaway from all of this. When you're talking about arts parts to people, this is what makes it weird, is these zinc lead microspheres arranged in very specific patterns. Slag is not going to do that, folks. Here's all the links. Leave those up for a second. And when you visit this presentation, if you look in like the comments section or the notes section, I have some additional links that I couldn't fit in this single slide. That's what I got.